attention. Let's get started. Welcome back, guys. Let's settle down. Welcome back to 453 after the break. Boy, it feels like I haven't seen you guys in a long time, but it's actually only been 3 classes or 1.5 weeks. I think more than 3 weeks or something. We're going to look at how PCB works finally today. Okay? I'd like to spend a little bit of time also on some administrivia, similar to first class day, but laying out what to expect for the second half. I also sent a post about it, so it's largely a reminder to go read the post carefully. And I'll spend the last few minutes on project 1B Q&A. I have office hours right after, so I'll let it stretch for a few more minutes if needed. After class, those of you who have to go to another class, feel free to leave at 2:15. But I'm happy to stick around and answer more questions. This is the last class, I think, before it's due. Okay? And lab 4 is being posted. It's due, you have at least a week, so it's due in a week or so. It's posted on Piazza. I'm always a little surprised at a couple responses, at a couple posts, messages I get on Piazza saying, I completely had no idea this assignment was due, I missed the deadline. That's the purpose of this. Every single class, I tell you what's going to happen in today's class, and anything that's due that week, it will be noted here. So, in case you missed it and these are all pinned posts, all assignment release posts are pinned posts on Piazza when they're due or after release until they're due. I mark an option saying you're required to read it before you make any post on Piazza, so I think it should be enforcing that. And even after all that, you missed this, you get a reminder in class. Just be on top of what's due when, okay? This is the easy stuff. Don't drop the ball on the easy stuff. All right. I'm curious, how was the midterm? Any comments? I see some sheepish reactions. Well, I posted the solutions. I'm pretty sure you wouldn't have had any time to look at it because it was just before class. But let's do a clicker question. Just a fun clicker question. That's your first clicker question. Just looking for feedback of your impression of how you did on the midterm. So this is how you did. So I did well. That is, well means better than I expected to do. I did as expected. I did worse than expected. This is your best guess of how you did. I'm just curious about your reaction. Okay? That's your first question. Give me an answer in 10 seconds. It can't possibly take more than 10 seconds. Okay. Well done. Just 85 students, or at least 87 clickers today. All right. I sort of expected this. Let's wait till the grading is done. First thing to note, like I posted in the grade the second half post, that's this impose? Okay. Well, you're probably not read it, but your job is not to read it right now. You just have read, thoroughly digested it. One of the things it tells you is, in case it wasn't clear or you sort of somehow missed this, you didn't have to do all of the questions to get the maximum score in the midterm. Okay? The midterm was set to be sort of like any 4 or 5 questions, or in the spirit of that, but actually giving you more flexibility in that you had a total of 120 raw points to get, and whatever you get will be capped off at 100. So if you got 105 out of 120, that's like saying you got 100 out of 100. 100 is the max. Okay. If you got 95 out of 120, it's like saying you got 95% because it's a 95 out of 100. Okay. So first, you were not expected to do everything. The midterm is long. It's the size of a homework almost. But that's the nature of the midterm. People actually do just as fine. Generally, the midterm scores are a little bit less, about 5% less than homeworks, but they are very good. Like I said, homeworks are excellent predictors. Midterm is time constrained, so you are going to be under, it's not going to be quite, it's time constrained, it's closed books, you don't have the same luxury of, all right, I haven't done anything, any reading, but now I'm going to look at the homework question 1, look up where in the textbook I should be reading through question 1. It's not an approach that works for the midterm. So midterm averages tend to be lower than homeworks, but fairly well correlated and not too much lower. Okay? And then you also have this this 4 or 5 like options. So don't stress yet. That's one of the things that this long post that you cannot really tell you. Wait until we're done. If you found it very difficult, probably everyone else did. It'll all get curved out, and your relative standing is what primarily matters. Okay. So I'll re-emphasize this. This is something that these are grade boundaries or approximate grade brackets. Some people, again, it's about time. The second half, you wonder also, how am I doing in this course? Like, what grade can I expect? Right? This is something I stated in the very first class day as well, but we never actually saw it explicitly written down. People may have forgotten, some people may have not even attended the first class day. So here it is explicitly. I'm making sure I'm going over it despite posting, because I find that some people just don't read the other posts. Okay? At least a third of every class I teach gets one of the A grades, that is, which means an A or an A minus. Okay? Students are generally relieved to hear this. I think this is at least as generous or more generous in terms of in grading than the average computer science course. I may be wrong on that. I'd like to get your opinion on that as well. It's a lower bound, not an upper bound. So the motivation for the lower bound is, if I cannot get a third of the class to get one of the A grades, then it's more on me than you guys. Okay, so I will make sure that that happens, right? You did about as well as one could be expected to ensure that that's a lower bound. It is not an upper bound. So it is possible for every single student in the class to get an A. It almost never happens, not in large classes like this. But there's nothing fundamentally preventing that. There's not a curving I impose to say that there's a maximum number of A grades that can be assigned. Okay. These are really thumb rules. So what else? So not everyone's going to get one of those A grades, of course, right? Especially in a class as big as this. The only other thumb rules I can give you, or guidelines, heuristics, is more among the people who don't get one of the A grades. That's at most 2/3 of the class. Typically it is lesser. More will get one of the B grades than any of the lower grades. So you're going to see sort of very likely A's are going to be very likely the largest number, followed by a smaller number of B's, followed by an even smaller number of lower grades. I think most CS courses grade tougher than this, okay? That should give you some optimism and hope and positive feelings if you're feeling underconfident about it. Okay? You can work. This course is structured so that it's not like your algorithms course. It's not like one of your theory. It's not hard in that way. It's structured so that a lot of it, if you simply just go through the motions, like labs especially, 10% of class credit, right? Class participation credit. And like a good fraction of even homework questions that are just identical, or exam questions that are literally identical or near identical to the ones we've seen in class. You just go through the motions and get those right, it's possible to do quite well on this course, okay? It does happen that, people bomb an assignment here or there. They just blew it because, I don't know, they missed the deadline or something came up or all kinds of things happen. There'll be options for extra credit, optional extra credit. That's one of the things this tells you in April. What that means is it'll be a homework or lab-like activity where you can say, okay, I screwed up on one of these things earlier. I had this or I had that, or I fell sick, but I really didn't have any documentation to support that, and so I can get a certain exception. You can use optional extra credit activities to make up for it. The way that's going to work is it's truly optional, and it's extra credit. Optional means if you're doing fine, you don't have to worry about doing more work, right? Than the 5 homeworks and 5 labs. Whatever is stated on the overview page. I think it says about 5 labs and 5 homeworks is the normal workload. But if you blew one of these or did poorly in the exam, you can use this extra credit activity to make up for it. So it's optional in the sense that if you choose not to do it, it will not affect whatever grade you would have otherwise gotten, right? No matter if every other student in the class decides to do it. The way it'll actually be implemented is, at the end, I'll figure out grade boundaries without counting any extra credit. So those grade boundaries will be fixed, and then those who get extra credit points will simply be bumped. Their grade can increase, but those who didn't do it is not going to change whatever it was from before. Okay, so it's truly optional in that way, but it helps students who are feeling especially anxious. It most helps students who are sort of on the boundary of pass-fail, they need this course, or like the C boundary or whatever is the minimum grade in computer science to count as pass. It particularly is going to help them. Some of you will want to just get the best grade they can. So even if you're on like, if you're getting B+, you just want to optimize it to A or A-, you can do extra credit and you'll get the same benefit, right? And if you choose not to do it, that's totally fine too. You will get whatever grade you were going to get anyway. I saw a couple of things, yeah.
What percentage of the grade will the extra credit be worth?
Oh, I haven't. It's a little hard for me to say right now. It'll be the weight of it'll be between a lab and a homework. That's the extra credit activity, and then there'll be an option. You can either choose the lab or you can choose a homework. Okay, it's not just TBD the schedule. I sort of look at the class's performance before deciding that as well. There's also a programming assignment, extra credit options, although this is less likely to help people who are not doing that well, okay? So in programming assignment 1B, there's some part of the credit of the points that are for speed, right? That doesn't mean that you have to be among the fastest small few percent to get that credit. That's not how it works. The faster you are from a really slow client-server option all the way to the fastest possible, actually not the fastest possible, the baseline level of fastness we expect most of you to get, your points will be distributed based on speed, and then a smaller fraction, something like 10% or less of the class, where the fastest clients on the leaderboard will get extra credit points, which is sort of, again, topping off points on top of 800 score. Okay, so if you do really well on project 1A, again, if you've been blowing assignments and homeworks and exams, it's possible, but less likely that you're going to be one of the best in one project 1, right? But those small numbers, students will also, those points will count as extra credit. So you can put in extra work in assignments if you feel like exams and homeworks are sort of not your best forte, you can code really well, right? Same thing with programming with project 2. There'll be a leaderboard in project 2 as well. So the fastest times there as well will get some extra credit. So these are all the various options for extra credit you have to sort of do more to improve your grade if you're very anxious about optimizing your grade, or even just meeting the passing cutoff.
Wouldn't there be a difference in running time based on what language you submit your code in?
Let's, because I want to get TCP done, let's wait till for the project part of the class again. Anything about just administrative, like grading and I think I covered the midterm stress. Oh, I am curious, what percentage of your other CS courses is not going to affect how I do grading? So I'm just looking for an honest opinion, your opinion here. What percentage of your CS courses typically you think, or what percentage of the class in CS courses you think gets one of the A grades? So that's an A or an A minus. And the options are about 10%, about 20%, about 30%, about 40%, and about 50%. I'm pretty sure not more than half the class gets one of the A grades in pretty much any core computer science class. So give me answers. Can I just get a poll for your response to this question? Sorry? That's fine, you don't have to answer if there's no guess for this. How? Instructors don't tell you this information? Okay, well, you get this information in this class, right? All right, I think it's more than enough time. 30% is the most common. My guess is this seems like it's just a random number selection really. Most instructors, other instructors don't actually tell you this information. So I'm not sure. I'm going to just take a screenshot of this. I'm not sure like how much weight is assigned to this poll. But I was just curious in any case. It's not, I don't plan to use numbers in any specific way. Yeah, finally office hours, you're welcome if you're particularly anxious in the lower quartile. Moodle shows you, I believe, I don't see what you see on Moodle, I believe Moodle shows you where your ranking is, relative ranking is in the class. Or it used to show at least. And so that combined with these guidelines should give you a pretty good projection of your final grade. This is, of course, assuming that you'll perform exactly as you've been performing thus far. That you will perform better or worse than you say. All right. Any other questions? All right, let's switch gears. Switch to looking at how TCP actually works. What we've seen so far, what we saw thus far is a sequence of these RDT protocols, reliable data transfer protocols, that showed us principles of very simple stop and wait protocols. Send a packet, get done reliably transferring the packet, then move on to the next packet. We saw how to do that under various channel assumptions, corruption only, corruption and loss. We didn't really see how to kind of reorient there. And then we say, okay, this is fine for toy protocols of really understanding the basics with an emphasis on correctness first before performance optimization. But in practice, we care a lot about performance. We want fast protocols. We can't stand it when our downloads take really long, right? And so pipelining is the top level, the biggest optimization you can do. Instead of sending one packet at a time and getting done with it, wasting most of the time that packet takes to propagate and that ACK takes to propagate, propagation delay, speed of light delays, you could be just sending more. You'd be transmitting more from this transmission, remember, is an endpoint activity. Propagation is along the wire. So pipelining gives us a lot of benefit, but the moment you introduce pipelining, protocol becomes more complicated, and we saw two classes of protocols, go back and selective repeat. If you're not familiar with that, you studied about it for the midterm as well. And now we're going to move on and look at, sorry, I'm on the wrong slide. Oh, well, one of these questions was momentum. Well, we got the solutions now. Now, so we saw go back and selective repeat. We saw that go back and, this thing just takes a while. Go back and uses cumulative acknowledgements. So if you get packet 24, and then you get 27 and 28, you're still, the receiver still sends at 24, at 24. You keep sending at 24 for every new packet until 25 arrives, at which point it will send at 25, or whatever point until which it has cumulatively received everything. Selective repeat does not do that, right? Selective repeat just has an independent acknowledgement as well as an independent timer, one each for one packet. TCP supports both, but it largely is more similar to go back end, or the first versions of it were go back end. The default version is still go back end. There is a selective repeat-like option in TCP. Okay, we'll look at all this in much more detail. So what is TCP? Well, before even looking at how TCP works, which is really just putting together most of these concepts we've already learned into an actual design. Let's look at the features it's providing you. Okay, it's actually providing you more than what we have learned in the principles for this chapter. So it's a point-to-point protocol. Okay, there's two endpoints, so it cannot be used for multi-point-to-point or multi-point communication. BitTorrent, for example, is a point-to-multi-point or multi-point application level protocol, right? This is the transport level protocol. This is point-to-point. We understand now what this means, reliable in-order byte stream. Okay? We've learned it at least the hard way, if nothing else, through 1A. The byte stream, the reliable in-order byte stream is guaranteed to deliver every single byte reliably in the exact order in which it was sent, but there's no guarantees of when these bytes will arrive and in what bursts they will arrive. Just because you say sock.receive 1024 does not mean you will get 1024 bytes. You would get less, you cannot get more. Okay? So if you say sock receive 1.1024, you've seen in project 1A that you're not guaranteed to get the entire header. You may get more than the header, you may get exactly the header, you may get less than the header. This was also one of the homework questions. Some of you discovered it the hard way, right, by doing it and sort of assuming that if I say sock 1024, I get exactly the header because that's what you got a few times. And then when it doesn't work, you are trying to debug why it doesn't work. Well, that's the property of the socket API, right? That's why it's so important to read the documentation of whatever method in whatever language you're using. There are some socket API methods that will completely read it that many bytes and block until they read that many bytes, right? So if you're using one of those, that's a correct assumption on that usage. You got to read the documentation carefully. Anyway, so TCP gives you this reliable byte stream abstraction. It's very hard for TCP to guarantee that you will get a certain number of bytes, or if the sender wrote these bytes in this burst, the receiver gets it exactly in those kinds of bursts. There's no point in maintaining all this. Byte stream is the most natural abstraction. They'll just trickle in whenever. Full duplex, it's really bidirectional. The protocols we've seen involve a sender and a receiver. We said this is the sender, this is the receiver. In TCP, there isn't really a sender and a receiver. It's just a two-point protocol. They're running the same code. They're both senders and they're both receivers at the same time. Who is sending data right now? Which endpoint is sending data right now? It really depends on whether it's a download or upload happening. Sometimes both could be happening, right? If you're doing like a text message like chatting, where messages are going both ways over TCP, well, either endpoint might decide to send data at any time. TCP supports this bidirectional communication. It does use cumulative acts, just like in go back end. We're familiar with that. At the implementation level, there's a small difference in how we have conceptually seen cumulative access and go back in, and how TCP does. TCP implements cumulative acknowledgements. We'll see that in a second. It is a pipeline protocol like go back in or selective repeat. It's not a stop and wait protocol. It is connection oriented. We know this, unlike the connectionless UDP or datagram protocol, right? It's a connection oriented byte stream protocol. It is flow controlled. It should also say congestion controlled somewhere. Yeah, it's flow controlled, which we'll see shortly, is a provision for ensuring that you're not overwhelming the receiver. The receiver is not powerful enough to swallow this gush of data stream that's being thrown at it. The sender will automatically slow down to match pace with the receiver. UDP has nothing like this, right? The sender doesn't really have any receiver state. You're just throwing a datagram, independent datagram after independent datagram. Okay, this is the TCP header. Another thing. You're not expected to remember header structures, okay? Like I said, I did actually mean that the course, very little in this course is going to be memorization based. But questions like name 2 headers in this protocol, or name a header in that keyword in that protocol, I don't think of these as memorization questions. If you understand like what a protocol like UDP is, as opposed to an IP header, or what a protocol like HTTP does, you must be able to remember 1 or 2 things about it, right? So you're not expected to memorize these things. But what I'm going to show you here is the full TCP header. We don't see toy headers here. This is the actual header in every TCP packet that flows on the internet or in local area networks. Lab 4 will also make you've seen some of this anyway through Wireshark Labs. Lab 4 will explicitly make you focus on the TCP part of it, okay? All right, so what does TCP have? Like UDP, it has source port and destination port. Transport protocol generally has source and destination port. Port numbers are endpoint identifiers at the transport level. IP addresses are endpoint identifiers at the network level. Transport is higher than network, okay? We have a sequence number. Why did we need sequence numbers? Why did we need sequence numbers in reliable transport protocols? To disambiguate retransmitted data from duplicates in the data itself, right? If any protocol, unless it's a perfect channel, has to rely on retransmission. If you retransmit, you need to disambiguate between those two, for which we need sequence numbers. So we have a sequence number here, 4-byte or 32-bit sequence number. We have another sequence number, essentially, that's called the acknowledgement number. This is important to understand what this is. The acknowledgement number, as well as the sequence number, are both counting bytes. So it's the byte number. It is not a packet number. So that's one implementation that means we can go back and select a repeat versus TCP. It's a byte stream. It's telling you up to what byte something is being received, or something is starting from what byte something is being sent. So this sequence, oops, sorry about that. The sequence number, as well as acknowledgement numbers, are counting bytes, okay? So they're not counting packet numbers like in go back in or select a repeat. What is the sequence number? The sequence number, whatever number is here, let's say the number here is 42 right now. What that means is that the first byte in the payload, which starts after the header, this byte number is 42. This number is 42. That's what the sequence number means. The byte number and the first byte in the payload. Okay, so this is similar to body byte offset in file or something in project 1. It's saying in the file like what byte number that byte starts from. If you're trying to do a reliable byte stream, you got to specify where in the byte stream the sequence of bytes belongs. That's what it's specifying, right? The acknowledgement number is also a byte number, but it is saying what the byte number or sequence number of the next expected byte is. So it is information that's coming in a TCP header from the other side. This sequence number is the information that is being sent to inform the other side by the sender of that data. The acknowledgement number comes in from the other side as part of the acknowledgements of that sent data. Both are present in every packet because TCP is bidirectional. Both sides could be sending or receiving at the same time. The acknowledgement number is saying that this number is the byte number I'm expecting next. So if the acknowledgement number has the value 23, its meaning is somewhat similar to act 23 and go back in or select or repeat, or actually go back in. But in implementation, it's different. Act 23 means the receiver is telling you, I have received everything up to byte number 22, I am expecting 23. Act 23 means give me data starting byte 23. It does not mean I received everything up to byte 23. It means I received everything up to byte 22, give me 23 onwards, is what the acknowledgement number means. Okay? So these are implementation differences, but the essence, the conceptual idea is these byte numbers, the sequence number is cumulative, it's counting bytes, and the acknowledgement number is one more than the cumulative number of bytes that have been received at this time. Okay. Clear? That's your actual payload. This could be a variable length. You have a checksum. We saw this existed in UDP. Same checksum as in UDP. One's complement sum of 2 byte words, if you remember. And then there are TCP supports options. Yeah.
I get what the acknowledgement number is saying, but what is the A bit character supposed to be? I'm confused with that.
Oh, yeah, sorry, I skipped over that. That whole half row or 16 bits or 2 bytes, it's a bunch of flags and some other information. I'll touch upon the details of those. That specific flag A is simply saying that this packet, if the flag is on, is true, it's 1, that bit is 1, it's saying that this packet is an acknowledgement packet only, which means it doesn't have any data, it has a 0 payload. So for example, at connection initiation time, you send a SYN, you send a SYN-ACK, these are payloadless packets. So a SYN-ACK is simply just acting the SYN, it doesn't actually give you any data, right? I think you should know what these SYN-ACKs mean through Wireshark lesson before, but if you don't, Lab 4 will make you actually do it. We'll also look at this in more detail later in the class. Later this class or next. Okay, so that's just saying that this is an ACK, so there won't be any payload associated with it. What else do we have? Length. That's So that's telling you what the length of the header is, okay? Sorry. So that's your header length, because header length can be variable. Unlike UDP, TCP supports options, so it's not a fixed length header. This up to here is fixed. I haven't told you what these are yet. But there could be a variable length options, and then payload actually starts from here. So the header length will tell you where the payload starts and where the header ends. So for example, in project 1A, at the HTTP level, we said header stops when you have 2 successive new lines, not 4 lines. That's not meant to be hard-coded. The description tells you 2 successive new lines marks the end of the header. It's a variable length header. In TCP, that length is explicitly specified. There are some bits that are not used, and then there are these other flags called the reset SYN or SYN flags. These are used in connection management, opening a connection and closing a connection. We'll see how these are used. It doesn't make too much sense to go too deep into it now. That's for flow control, okay, receive window. Remember in go back and select or repeat, we said there's this number n. That's the most number of outstanding packets I can have. And we just said, we know this somehow, okay, this n. Somehow, this is a fixed number, and we can send no more than this number. Where did this number come from? Well, there has to be some limit on how many bytes you send outstanding, or how many packets worth of data you send before anything is acknowledged from the other side. Because otherwise, you're just throwing data into the network, overwhelming it. You might be overwhelming the network, might be overwhelming the receiver. In order to ensure that the receiver is not overwhelmed, there's an explicit feeding called the receive window that comes back in every response from the receiver, telling the sender what's the maximum window size it can use, because if it uses more window than that, then this receiver it just cannot swallow stuff at the rate that the other side is throwing it. Okay. So this is one parameter that feeds into the N in go back in like protocol, or selective repeat like pipeline protocol. This is not the only one. You should also not overwhelm the network, but that's not sort of in the TCP header. We'll see how TCP actually does rate control to not bring down the entire network. It has, if abused, it can bring down entire networks. That's called congestion control, which is different from flow control. All right. There are some of these pointers, like some of these flags, like urgent. This urgent flag corresponds to whether there's an urgent data pointer or not. They try to some of these circumvent TCP's byte streams to push data that's more urgent to the front, but these are not used in practice. So you don't have to really, these just existed at design time but are not used in practice. You don't have to really worry about this. Most of the other fields, sequence number, receive window, checksum, let's not count the options either because they're a special case. These are bread and butter ingredients of the TCP header. We have a pretty good understanding of why all of these are needed, right? So at least the sequence number, checksums, and so on, and source and destination port, of course. Okay, so how does TCP use this information in the header? So this picture looks very much like go back in that there's a set of green packets. These are packets that have been successfully acknowledged, cumulatively acknowledged until here. This is the first packet that has been sent but not acknowledged, just like in go back N. These are packets, just like in go back N, that can be used, or bytes actually that can be used, but haven't been used yet. These cannot be used because the window limits what you can use. One ingredient of determining that window is the receive window for flow control. It's not the only one. So you already know this, the byte stream number of the first byte in the segment. Act is saying, give me this byte. That is what the act number means. What happens if, in TCP, if a receiver has received everything up to byte number 2340, 2340, and then it gets it's next expecting 2341. But instead of getting some bytes starting from 2341 onwards, it gets 2782 onwards, some 100 bytes, 2782 to 2881. What does it do with these out of order packets? Well, the spec doesn't really say what to do. Just like in go back N, not selective repeating, just like in go back N, the receiver may choose to buffer these packets or rely on the sender to retransmit them anyway. Keep in mind that go back N protocols forced the sender to retransmit everything starting from this place if the timeout happens. The timeout was actually for this packet. In TCP, it'll be for that byte onwards, because it's counting bytes, not packets. So, in practice, of course, TCP receives do buffer out of order data, because if the data is out of order just because it got out of order in the network, this can happen sometimes, especially if packets happen to take different paths, but sometimes even if they take the same router level path, they can get out of order. Then you might as well buffer it, because if you drop it, you'll necessarily force a timeout. But if you buffer it and then the holes get filled up, then the sender may never come out and need to be transmitted in the first place. So buffering in practice is done, but it's not necessary for correctness in TCP. Okay, so here's an example of how TCP sequence numbers work. This is most of these protocols we see examples in code as well of echo protocol. So capitalizing is like the capitalizing server that we saw for TCP. Unity is sort of like that. Just capitalize. Here is an echo server that echoes one character at a time. Okay, so we want to make sure we understand what's going on here. Oops. What's going on is the sender types a character, the receiver echoes that character, the sender is then going to act the receipt of the echoed C and so on, then the receiver is going to echo that character and so on. So when the user types C on host A, it is sending a packet with a payload that is 1 byte. Okay? ASCII characters in pretty much any encoding are 1 byte. I'll touch upon encoding a little bit at the end of this class because it's relevant for you. It was relevant for 182, as some people didn't notice. You may have gotten your code to work even though you made this encoding particular mistake. But anyway, here, one character is just 1 byte. It's an ASCII character. The payload in the TCP payload has just 1 byte. It is saying that is byte number 42. It's the 42nd byte that host A punched in from this side. And it also, that packet also has an ACK number of 79, which means host A is saying, I am sending you byte number 42 with this byte C. I am expecting from you byte number 79 because from you I have received everything up to 78. Give me 79 onwards, is what that first packet means. When the receiver gets this packet, it is going to echo this packet with the same character as it received. Whose sequence number is of course going to be 79, the next one that the sender is expecting at this point. No losses are happening in this example. Everything is going reliably. This is a good case. So the receiver's response, the echo, has a sequence number of 79 and an acknowledgement number of 43, which means the receiver is now saying, oh, I got your 42nd byte, give me 43 onwards. Okay, so this is exemplifying what we just saw as the meaning of sequence numbers and it goes on like that, 4380. What's going to be the next one? What's going to be the response of 4380? Okay. What sequence number and acknowledgement will be the response? There's one to this 4380. Yeah?
Sorry, 6 would be 80 acknowledgement.
44, 80 and 44, right? So the sender is asking, give me 80, so the next byte will be 80. And the receiver will be asking for, give me 44, because it asked for 43 earlier and got 44. Good. Okay, so these are really implementation differences, but essentially it's a go-back-in protocol. It's counting bytes, not packets, and it's off by 1 in the nature of interpreting what the acknowledgement number means. Okay, timeout. Okay, TCP timeout, not class. We need timeouts. Why do we need timeouts? Loss. If there's only corruption, it means if the sender sends something, the receiver will always receive something. It could be garbage, corrupted, but it will receive something. That world is easier than sender sends something, nothing reached the receiver. We saw that RDT 3.0 was more complex for this reason. It used timeouts. TCP has to use timeouts because it tolerates corruption, it tolerates loss, it also tolerates reordering. Okay, a lot of reordering. Ultimately, yeah.
For the flow control setting that we saw before, is that like a manually set parameter, or is that like controlled by an algorithm, like dynamically?
Dynamically, we're going to see that in a few slides. Okay, so we don't know. A sender doesn't know beforehand like how powerful, how quickly the receiver application can read. Right? So you think about this in your project 1 as well. You're writing a receiver, right? A client. I mean, your client is both a sender and receiver. You're sending commands, you're receiving data. If you don't read fast enough from your receiving, from your side, your client side socket, the sender is not going to keep on dumping data into your machine, arbitrary amounts of data in the machine. Well, the files that you're playing with in the project, they're fairly small, so they can all be dumped and be stored in the machine. But if the file was, let's say, a terabyte in size, There's no room, there's no memory to store. There may not be even memory to store this much. Socket default maximum socket buffer sizes don't even go to like gigs and stuff. So how does the sender know, the server know that you're overwhelmed? We're gonna see where that's done dynamically. It's a fairly simple process. We're gonna see that in detail. So we need timeouts to tolerate losses. We saw that timeouts are a trade-off. The value of the timeout is not important for correctness. So you could have just a 1 nanosecond, a zero timeout, if you will, and keep on retransmitting a packet until you get an acknowledgement. That's just a stupid thing to do. It's inefficient, it's wasting resources. You can have a very long timeout. That is, you can say, I'm going to give it a long time. I'm going to give this packet an hour to get to the West Coast, okay, and get back the acknowledgement. That's clearly too much. We see that ping latencies to the West Coast are like 80 milliseconds or 90, 100 milliseconds. Maybe a delayed packet might be 200, few hundred milliseconds. An hour is like 3,600 seconds. That's too much, right? If you wait that long, you're blocked without being able to make progress until you fix that gap, because it's a reliable byte stream protocol, right? You have to fix a gap in order to be able to, with the other end, to deliver that data to the application. So we need a timeout that balances these two constraints. Don't retransmit too soon, because that's just a waste, and don't wait too long, because that's going to again slow you down. That's also a waste for a different reason. What's a good timeout value? Well, a good timeout value is one that balances those two constraints. So it makes the likelihood of detecting an actual loss very high while reducing the likelihood of false positives. That is, if a packet is just getting delayed, but it's not actually lost, you don't want to prematurely declare it a loss. There's no like one optimal magic value of a timeout to use. It depends on how much variation there is. So let me show you a pictorial example. TCP uses a method called an exponentially weighted moving average. Right, so this picture shows you there was some way to quickly switch between slide mode and non-slide mode. So when we do our pings, I forget which one was not actually on the West Coast. Okay, this is not going to the West Coast. How do I know it's not going to the West Coast? It's impossible for light. This is faster than the speed of light to go to the West Coast and back in 15 milliseconds. So UCSD clearly is not using. It has a mirror surface somewhere on the East Coast, or somewhere much closer. Okay, so Berkeley is probably going to actually going to Cal. So you see variation there, right? Much of that variation, it's a 1 or 2 milliseconds right now. It could be more just because of the Wi-Fi variance. It could be even less. Occasionally you may have a lot more, like this one is 400 milliseconds, right? If you look at this stuff ticking by like that, I mean, if you look at stock tickers, right? Stock prices, they're also moving like that. There's fluctuation. There's fine-grained fluctuations in the course of a minute, in the course of an hour, in the course of a day, in the course of a week, in the course of a month, in the course of a year, in the course of years, in the course of decades. You can zoom in at different granularities and you will see fluctuation, right, in stock prices, not this kind of thing. The same thing for temperature. You're looking at long-term climate changes, fluctuations are happening at different scales. This is all streaming data. Streaming data, when you deal with streaming data, it often is very, very useful to get a sense of the moving average. The moving average is just like an average of a set of numbers, but it's moving over its computer over streaming data. If somebody asks you, what's the average ping round per time? If I stop this thing gives you an average here. You're all familiar with ping because you've used it in labs and stuff. So it tells you the average is 122. Well, the average is influenced by outliers so bigger values. That's why the average is 122. Fairly more than the most common value, which is around 80 here. So this is an 87 packets, over 87 packets, the average is 122. But if I have streaming data, there's no number of packets. The number of packets is changing over time. And I asked you, what is the moving or dynamic average? How would you compute an average for streaming data like this? Yeah?
Use a window.
That's a good, what's your name again?
Lenny.
Sorry, say that again?
Lenny.
Lenny. So Lenny's answer is the window, right? Yeah, you can do that. So you can actually pick the window to be, let's say, 87, the number of packets in the previous thing. But if you choose the window to be, let's say, 10 packets, okay, you'll get a very recent estimate. If you choose these 10, you'll obviously get a very high value that's probably not representative. If you choose a very high value, like 90 packets, the last 100 packets, you might be incorporating some very old information that's no longer relevant. So picking any value of that window, what value do you choose? Do you pick 10, do you pick 100, do you pick 500, do you pick 15, do you pick 3, what do you pick? That depends on like, how much weight do you want to give to data that's very old? Like at what point do you say data is very old? We want to just not count it, right? If you want to know the average stock price of the S&P 500, well, you can go decades back to the early part of the 20th century. At some point, or maybe the Dow existed and S&P didn't exist at that point as an index. So let's say the Dow, but most people would agree that the Dow index value in the early part of the 20th century has no relevance, no interest to anybody who's investing today, right? So you don't go that far back. So how far back do you go? Well, do you go like a month back, 2 months back, 10 months back, a year back? Yeah, at least a year back, because things can happen in the time scale of years. Probably a decade back to get a good idea of roughly where the index is at the historic time scale. So it's not easy to choose just one hard-coded magic number as your window. Yeah?
Instead of using a window, you could just like weight based on the time, like give the older values a smaller weight, and the newer values a higher weight.
Yeah. That's exactly what TCP does. Ideally, you want to give, you don't eliminate the magic number problem, you still have some magic numbers, but you alleviate that problem. You give more weight to more recent data and less weight to older data. And there's a specific way of doing this. It's called, of computing such a moving average, it's called the exponentially weighted moving average, EWMA. TCP happens to use this moving average, but it's just a moving average, right? Oops, what did I do? It's a moving average technique. It can be used for any kind of streaming data, any context in which temperature or stock prices, CP data, just any place you have streaming data, and there's any number of applications that have to do with streaming data, you can use this exponentially weighted moving average that works, that computes the current smooth round trip time, or which is called the estimated round trip time, also called the smooth round trip time. If you look at Linux code, it'll be called smooth RTP. Same as estimated RTP. It's computing a smooth value as 1 minus alpha times. This is basically an assignment. It's saying update estimated RTP. So there's like an assignment here. 2, 1 minus alpha times the immediately previous value of that estimated RTP plus alpha times the most recent sample RTP. Where alpha is 1/8. So it is giving 1/8 weight to the most recent sample and 7/8 weight to history, which doesn't seem unreasonable. You just get one sample that's very high or very low. You don't want to bet the house on that sample, right? So you give it a smaller weight, but you rely on history. So if the most recent sample was 100 milliseconds, let's say, and over time the average has been 80 milliseconds, then this formula would say the smooth RTP is 7/8 of 80 milliseconds, which is the current smooth average, with 1/8 of, what did I say, 120. This is the current, the most recently received sample. So if one sample happens to be too high, fairly higher than the moving average that you're maintaining, it will get a smaller value than the historic average. Okay. Why is this called the exponentially weighted moving average? What is exponential about this? This just sounds like a linear combination. It is called exponentially weighted moving average. Yeah.
Because you're like repeatedly multiplying the whole data by 1 minus alpha.
It's exponential in that 1 minus alpha. Actually, that's the base of the exponent. It's exponential in that it's giving exponentially lower and lower weight to older and older samples. Exactly what Nathaniel's original idea was for this body. How do we see this? What is estimated RTT? We're going to start by saying E0 is equal to, or let's say just E1 is equal to just sample 1. We don't have any samples from before. We can also assign E0 to be a constant and E1 to be a non-constant value. So we can do this way. Let's say we assign E0 to 1 second because we don't know what the value is right now. Then we say E1, the first estimated RTT when we get the first sample is equal to 1 minus alpha times E0 plus alpha times the first sample that was received. So far, nothing looks exponential. That's a linear combination of the previous estimate and the most recent sample. Weighted as 7/8 and 1/8. 1 minus alpha, alpha. Okay. E2 is equal to 1 minus alpha, E1 plus alpha times S2. Which is equal to 1 minus alpha times 1 minus alpha times E1 plus alpha times S1. Because I took this and put this here, plus I put this here, which is alpha times S2. So if you expand this out, you see a 1 minus alpha times 1 minus alpha, which is 1 minus alpha squared. If I keep writing this out, I will find that, so E2 has a 1 minus alpha squared and 1 minus alpha times alpha and alpha. I keep writing it out like this, En, after n such samples, the first term will be 1 minus alpha to the n of, sorry, this is easier. Because I just took that expression and put it in parentheses. Right? If you went to En, it will look like 1 minus alpha to the n E0 plus a whole bunch of terms expanded out. What is this saying? The oldest sample, which in our case was in this example is a constant, is exponentially being weighted down. After n samples, the weight of this old sample keeps exponentially going down as 1 minus alpha to the n. As n keeps on increasing, 1 minus alpha to the n approaches 0, right? Any value less than 1, you keep exponentiating it with a bigger and bigger exponent will eventually go to 0. So its weight is exponentially decaying down to 0. That's why it's called EWMA. And that's an example of how the smooth RTT will look like. You can see in this picture, there's a lot of variation, just like we saw, but the moving average is a lot smoother. The moving average, of course, will also have some variation, it won't be a straight line, right? But its variation is a lot smoother and the more bursty nature of the raw stream. So that's EWMA. 201, I still have some time. Okay, that doesn't say, oops. Yeah. That's just a moving average. That's not saying PCP uses the moving average is the timeout, the moving average. The average is the average, that's a typical sample. The average means that's what you expect a typical sample to take. So if your average is 100 milliseconds, you can't use that as, or you can use that as a timeout, it won't be incorrect, but probably not the best idea to use it as a timeout. If the average packet can take 100 milliseconds, some packets might take 110, some might take 120, some might take 140, right? So saying that setting the timeout to 100 is probably not a good idea. You're being sort of too impatient in your timing choice. TCP looks at both the average and how much there is deviation from the average to get a pretty good estimate to come up with a line somewhere, not this line, okay, just somewhere to say that if it crosses that line, the likelihood that it's an outlier is very small. And there is 99% chance that the packet is just lost. In order to do that, it has to compute both the smooth average and the deviation of the underlying sample. To compute the deviation is just a standard deviation. But familiar with the standard deviation, right? It's the square root of the sum of the deviations from the mean squared, right? That's just your standard deviation formula for the average divided by the number of samples. But we don't have a window here. We don't have a fixed number of samples. So how do you compute the deviation? We compute the deviation also as a moving average. And that's computed by with the same formula as before. I don't see that stuff, but you guys do. Yeah, I don't know how to move this. Never mind. Okay, well, it's the same formula. It shouldn't be too hard to read. It's saying the did I move to? Yeah, so it is computing, it's using a combination of the smooth RTT, which is your estimated RTT, plus 4 times the deviation, which is denoted dev RTT here. It's like the standard deviation, but we compute the deviation also as a moving average. I'll show you in 1 second. That is computed as follows. So 4 standard deviations of variation from the mean means the packet is almost certainly lost. If the distribution of timeout values was normally distributed, 4 standard deviations is already sort of 99.99 or more percentile, right? We don't know what the distribution of these values is, but 4 standard deviations is just TCP. Like I said, there are going to be magic numbers here, right? We have fixed some numbers, but instead of fixing a window size, we are fixing magic numbers like alpha, 1/8, 7/8, and then 4 standard deviations. That's TCP hard-coded numbers. You need to fix something, it is not an unreasonable choice, so we went with this choice. Dev RTT is being computed as an exponentially weighted moving average, exactly like the underlying average. 1 minus beta times the current estimate of the deviation plus beta times the most recent sample of the deviation, which is sample RTT minus smooth RTT, the estimated average. So the deviation is being rolled in as an exponentially weighted moving average. There's no n or a window size to compute the average over here. They're both moving, both the mean and the deviation. And the beta is 0.25. Okay, alpha is 1/8, beta is 1/4. Why? Why is alpha not 1/10? Why is it not 1/6? Why is beta not 1/3 or 1/5? There's no good answer. It's not an unreasonable choice. There's got to be something in a spec so that everybody implements the same protocol. These are the choices that are. If you change them slightly, nothing will happen. If you change them significantly, we'll have problems. Okay? Oh, sure. That good point. Remind me your name again? Omri, yeah. So Omri's point is the power of 2. That explains why it's say 1/8 versus 1/6 or 5 or 7, but what about 1/4, right, or 1/16? You're right, actually, it's a very important reason. The power of 2 is actually an important reason. These days it doesn't matter, but if you look at kernel code, you don't do divisions and any complicated operations inside kernel. So I'll show you Linux kernel code for how TCP is implemented, some important parts of it, for you on Tuesday's class or maybe on Thursday. You'll see that they're highly optimized. Power of 2s is why is it easy to deal with power of 2s? Because halving or doubling is just a bit shift. It's a very efficient operation. Yeah, so it still doesn't explain why 1/8 as opposed to the other powers of 2. At the end of the day, the answer is that these are not unreasonable values, right? You want alpha to be comfortably under 0.5, right? You want to give less weight to, or fairly less weight to the most recent sample. You want to give the bulk of the weight to the historical. Okay. So TCP sender and receiver, how are they going to be working with this timer? TCP sender is going to create a segment. A segment is just transport level packet. The name we use, the jargon we use for transport level packet. This is the sequence number of the byte string number of the first byte of the segment. We know this. We start a timer if it's not already run. So if there's no outstanding packets, there's no need for timers. If there's any outstanding bytes at all, there's at least one packet outstanding with some bytes that were sent in it. We start a timer. We think of the timer as being for the oldest unacknowledged segment, just like in go back in. The timeout is set as estimated RTT plus 4 times dev RTT, the formula I just showed you. If a timeout happens, this is very similar to go back and retransfer the segment that caused that timeout, that first one. We don't know that that's the segment that got lost, just like in go back in. That could have actually gotten to the other side, but the next one could have got lost, or that one could have been delayed. It's just that the sender didn't get an acknowledgement covering everything up to that packet. That's what caused the timeout at the sender. If that happens, we're going to retransmit and then restart the timer. An ACK is received that acknowledges previously unacknowledged packets. So the first segment that hasn't been acknowledged cumulatively, an ACK arrives, the sender is going to update. When an ACK arrives, it may acknowledge not just that first segment, it may acknowledge a few segments worth of data. It may acknowledge, so this is byte number, let's say 2300. The receiver has acknowledged everything up to 2299, 2300 hasn't been acknowledged. The next segment is 2300 to 2400. After that, 2400 to 2500. An acknowledgement may come from the other side that says, ACK 3000, I've received everything up to 2999, send me 3000. Because a whole bunch of segments all got acknowledged, all with like just one number, with just one acknowledgement. So that's what this is saying, that it'll update what is known to be ACK cumulatively. And then if there's still any more outstanding packets, 3000 onwards, if there's anything sent, it'll restart the timer and think of that timer as being for the unacknowledged segments starting from the 3000 number. If there's no more unacknowledged segments, there's no need to start a timer. Okay, so that's how TCP is using timeouts. These are the events of the sender and receiver. These are 4 very basic event types, so it's a very simplified version of TCP. Even not counting flow control, condition control, and so on. An arrival of an in-order segment with expected sequence number, byte sequence number. That's the event of the receiver, and all data up to the expected sequence number has already been ACKed, up to, but not that expected sequence number. Then the receiver action is going to be a delayed acknowledgement. In TCP, there's an optimization called the Nagel's optimization. It's a delayed acknowledgement optimization, which is saying, don't send an acknowledgement for every single packet. Wait for some more data to arrive, and maybe acknowledge a few packets all at once, because cumulative ACKs allow you to do that. So the receiver is going to wait for 500 milliseconds for the next segment see if there's more segments that arrive in order. If they all arrive in order, then you can just add all of them in one fell swoop. An arrival of an in-order segment with an expected sequence number and one other segment has act pending, which means that you were in this delayed act mode, it's going to immediately send the single cumulative count. It's left out, it got everything as expected, so for just one act, it's acknowledging multiple segments, right? Or two segments in this case. Arrival of out of order segments, which is, I'm expecting this, but I get something out of order. This is a higher sequence number. That's a gap. The gap is detected, just like in go back and it's going to send a do act. If it's expecting byte number 2300 onwards, and it gets a segment with start with a sequence number of 2372, there's a gap of 72 bytes. It is going to send an acknowledgement saying at 2300, give me 2300 onwards, because that's what I'm expecting. It keeps getting segments without that gap being filled. It will keep on sending at 2300, at 2300. It's getting more and more new data on the other side, but it's not able to send you anything back other than at 2300, because it's saying, I am getting something, but there's a gap, and the gap starts at 2300. That's a duplicate acknowledgement. This is very similar to go back in, but counting bytes. The gap is filled. At that point, you immediately send an acknowledgement cumulatively. Okay? Alright, so I'm going to switch gears to some tips for Project 1B. Okay? The two most important tips, and like I said, I'll let it flow for at least for 5 more minutes after. People can feel free to leave or stick around. One thing to keep in mind, the 2 tips from Project 1A, absolutely you gotta keep those in mind. Okay? So, these were tips. Anytime you're using a method that you have never seen before, do not assume that you know how that method works. Read its documentation. The concepts of byte stream that you have learned are common across all languages. But if you write a piece of code, actually I think I have a piece of code. This is by far not the only example. Okay, I'm taking the liberty of using one student's code. I hope they won't mind if their name is, you can't see the name anyway, so it's fine. So here's an example of a piece of code. It looks pretty innocuous, it looks like code you've never written. But this is actually much better code than other pieces of code that I've seen where people would just write sock or receive 1024. You know now that it's not guaranteed to receive exactly the header, right? This is one of the things that the tutorial made you learn if you actually did the tutorial. This is also what the documentation of the method would tell you. Well, so what's going wrong with this code? This code seems reasonable. It is saying while true, data plus equals sock.receive 128, split data by searching for 2 new line characters. I mean, that's what my Java solution also conceptually did. Do take a look at that solution also. And then it's going ahead and doing len split data. It's basically seeing if the header has been read because this thing was found, so the len of the split is at least 1, then return the extracted header. This seems like a reasonable piece of code at first glance. Many of you probably wrote code very similar to this. There's a problem with this code. Can anyone tell me what the problem with this code is? Yeah?
What if the new line characters is at the end of one chunk, beginning of another?
Well, then it's just maintaining, it's just accumulating all received data until it gets 2 new lines. So that's a good guess actually, but that's not the problem. Omri. What's your name? The one who answered just now. Can I get your name?
Kelsey?
Kelsey, okay, so it's a good guess, Kelsey's answer, but that's not quite the problem. Omri or Nathaniel? Well, you don't quite know what's happening in this extract header, whatever the student has written. So we don't know what exactly is going on beyond. There's a just in these lines of code, we should be able to state a problem. Yeah.
Isn't it not encoded as a string, it's just bits or bytes?
Yeah. Does that make sense? A lot of you use this thing, UTF-8. Do you understand what this is? My solution didn't have this. Why did you use this, or why did you think you need to use? Do you know what you're using? Like, what is UTF-8? Why are you using this? You've just seen this type of code in other classes and things. Can anyone tell me what UTF-8 is? Yeah. It's what? Well, that's like saying what it stands for. But what is it doing? Yeah.
It translates the byte into UTF-8 form.
Whenever you deal with strings versus bytes, they are different animals. Okay? Strings and bytes, strings are sequences of characters. Bytes are 8 bits. Bytes are always 8 bits. Okay, a bit, if you know what a bit is, the 0 or 1. Strings are characters. Characters like A, B, C, ASCII characters, they're all represented using 1 byte in any encoding. There's no encoding where you need more than 1 byte to represent the most common characters. In general, going from a string to bytes, or going from bytes to a string requires an encoding or decoding. That's what this is specifying. I never specified that the encoding or decoding is going to be a word. So how do you know it's UTF? It's not. All you know is if you read byte by byte, when you get to 2 new lines, that's when the header ends. After that, it's not characters at all, it's just binary dump data. If you do this, if you forcibly read what you received as a string, then what's happening is you're reading everything. Let's say this is the header and this is the payload. This is where the payload starts. This is the header, so this is body, byte, offset, byte, and so on. And this is the first few lines, this is the fresh line. If you do receive 128 like it does, you may receive like this much of the data. By doing this split is a method that works on strings, not on bytes. You are telling Python, treat this whole thing like a string of characters, including some of the binary gum. That was never meant to be a string in any encoding. Okay? You're saying encode this whole thing, assume that this is a string encoding, some string, all these bytes, and try to decode it as a string. There's no encoding specified here. The student didn't specify any encoding, but whatever encoding he would have specified would be wrong, because it would be trying to parse these bytes as string in some encodings. So parsing these into a string and then going back later in the code, which he must be doing, not shown, going back from string to bytes will not give you back the same bytes in every encoding. You take some gibberish bytes, it may not even be convertible to any reasonable string in some encoding. If you go from string to bytes and bytes to string, not every encoding is guaranteed to give you back the original string. The one thing that you should know about encodings and decodings that is enough to do this project is not use something that you don't clearly understand why you're using it. And of course, the project is very easy. It just needs you to know that no matter what encoding in the world you use, ASCII characters like in the header are guaranteed to be 1 byte for 1 character. So you don't need any encoding. You just read byte by byte until you find 2 new ones. If you don't do this, you will have these kinds of bugs. People will say my code is blocked, it's stuck, it's not getting 10,000 bytes, it's not getting as many bytes I should get, it's getting a few less. It's because you gibberish out. You introduce a bug by treating these as a string and then going back to bytes. You cannot do that. Other questions? Yes.
But I definitely will be able to start this
You can do many of the things, but as long as you're not